to start with a kind of a like straw man that I threw out a few years ago. So I've got a browser. It's called Firetran. It's super fast. It renders pages 10% faster than Firefox or Chrome. And 10% is a big deal because those packages have put a lot of effort into fast rendering, but only if there's no JavaScript. And if you need JavaScript, you have to recompile. Not a big deal, right? Now the character encoding and the proxy configuration is compiled in for speed, you know. There's mutually incompatible forks, have some features, you know, with a plugin, for example, versus not. There's no confusing runtime proxy dialog, no like configuration, you just edit a file and recompile. For security, HTTP and HTTPS are mutually incompatible. Now, you've seen there's a lot of vulnerabilities on websites where like a secure page loads something that's insecure. We don't have to deal with that because it's not allowed. The address goes in a configuration file. You don't have any you know, location bar. You put it in the configuration file, run the executable, you get the page faster. There's a tickle script now because we found that that was kind of cumbersome. There's a tickle script that manages the configuration file, and there's a plan to extend the script to recompile Firetran with optimal features for each page. It's open source, but the development is private. So Firetran's struggling with market share, and this seems pretty silly to us, kind of, you know, looking at it. Why would anybody want a browser like that? And yet, this is startlingly similar to what we see in a lot of scientific software packages. And why do we tolerate it? Why is this somehow acceptable in scientific software, and yet totally unacceptable in, you know, software for the general public, software for business purposes, etc. Is scientific software somehow like uniquely different? And I'm going to argue, basically, no. This is a big failing in the way that we learn and kind of grow accustomed to software and the trade-offs that we're willing to make. Now, admittedly, things have gotten better since I introduced this parity. It's in a 2014 size paper, but it's still slow going. A lot of remnants of that persist. Part of the complexity that we're grappling with now is dealing with GPUs. And a few years ago, everybody was saying, oh, the future is exclusively GPUs. And now the top slot on all of the performance benchmarks these days is a machine with no GPUs. And so now people are rethinking this. Some people are still, oh, this was a, you know, last gasp of pure CPU architectures. But the thing is, there isn't a fundamental reason why GPUs are so vastly faster. And the A64FX, which is in Fugaku, kind of demonstrates that you can have good memory architecture on a CPU. And so this complexity is going to stick with us for quite a while. Probably there's no escaping it. And yet, for some applications, we're going to find that pure CPU is a really good choice. So I was part of the ACME project, which is now called E3SM, back in its early days. And so the project started around 2014. This is climate modeling from DOE. So basically, DOE forked the CESM, which is the community model that's widely used. And it's a very large project, over $20 million a year, a team of like over 100 people that are involved. And there was one performance objective, and it was maximize the number of simulated years per wall clock day at target resolution, because this is what's needed to do IPCC scale prediction. This is what's needed to inform decisions over longer time horizons of, you know, say out to 100 years. And so the target was 5 simulated years per wall clock day. And turns out that's still not achieved, even now in 2020. So at the time we were dealing with this, I threw out a prediction there. I said, no DOE facility through 2020 will run Acme faster than Edison. And this is from a 2019 paper, more or less demonstrating that that in fact is true. And so on the left panel here, this is sort of a measure of efficiency. And this is a traditional sort of scaling plot. And so we look over at the right side and we kind of see these curves crossing. So Edison, the green being the old machine, 2 versions of the code. Home XX was a complete rewrite. This is for the dynamical core. The full model has more complexity, but actually would accentuate this sort of disappointing result. And we see Edison scaling very well. Over on the right here, this is what people actually care about, so simulated years per day, and you can see the same sort of effect happening in that upper right corner. It's the same data, just plotted in a different way. So Edison is just a traditional, it's a, I think, sandy bridge architecture. The blue here is the Corey Haswell, which is doing better. Like over here, we can see that it's doing better, but they didn't build as many nodes of that because they did mostly KNL. Now, was my prediction actually true? Not quite, because BER started, so looking into DOE, there's the Advanced Scientific Computing Research Office, which is, that's what normally maintains the machines, does all the leadership class machines. And there's BER, Biological and Environmental Research, that's who is funding ACME, which is now called E3SM. Anyway, BER, the Biological and Environmental Research, started buying their own machines. And so, in fact, they have purchased machines. They have a new one going in at Argonne right now. And they're like 15 to 20 rack machines, so not small, not as large as the leadership class facilities, but quite large machines. They're buying their own machines in order to be able to meet their requirements. They didn't used to do that. It used to be that the Oscar machines provided what was needed. And so what's the fundamental reason for this? Well, latency and throughput are really different kinds of quantities. And optimizing for latency is not the same thing. You don't make the same choices in terms of an algorithm. You don't make the same choices in terms of hardware. And so this figure is sort of demonstrating this. And we're going to look at other plots that have this sort of structure. And so on the y-axis, we're plotting like a rate of computation, and sometimes it'll be a rate of computation per node. So it's a measure of performance, and higher is better. And on the x-axis, we're going to choose the time per like unit of computation, per time step, or per full multi-grid cycle or something like that. And so really you want to be over to the left and up, and that's what gives you capability. So looking here, we see if we need really low latency, then the Broadwell is delivering good performance here. However, if we're very patient people, I'm not a very patient person, but I mean, I can be when I have to be, but I don't like being patient. But if we're very patient, then we can perhaps get significantly higher throughput, and that just basically means we can make it cheaper by moving over here to the right. The thing is, you can always buy extra nodes. And so if you're willing to pay more, you can get performance for those larger problem sizes for these, for computing things that take longer. And so we can choose architectures that make this cheaper. Um, if we need high throughput um, and we're willing to be patient, then we can also just get that by paying more. Whereas for latency, there's no ability to pay more in order to get lower latency. That's a very limited kind of quantity, and it involves making these kind of hard trade-offs. So as an example of this, there's a sort of recent paper on near global climate simulation, and they drive it down just a hair under 1 kilometer. This is a model that from the group at CSCS, the Swiss Supercomputing Center, and their weather modeling group. And that model is called Cosmo. They did a rewrite targeting GPUs specifically. And they optimized quite well for GPUs. They didn't put nearly the attention into the CPUs, but they say, okay, well, the target resolutions are kind of in these ranges, right? Ultimately, they would like to be able to run these very high resolution models, like this one at 1 kilometer or this one at 1.9 kilometers. This is a replot of the data they have, but it's the same as the figure in the paper. When you run at coarser, at a coarser model, so this is like 19 kilometer resolution, here we can compare the P100, so GPU versus Haswell CPU. And we see that they cross over. And so if you use enough nodes, you get your fastest time to solution on the CPU. But if you're using many fewer nodes, you get more efficiency on the GPU. So that's kind of a familiar story. Now, the question you might ask is, what about these? What about these points? Are these the like target simulated year per day? That is, we wanted that simulated year per day to be 1 or 5 simulated years per day. Is that going to be stuck in this strong scaling limit, or is that going to be something that's limited by throughput? And on this kind of diagram, it's kind of hard to see that. And you can look right here at the sort of intermediate resolution. This was the 3.7. And you might say from that 3.7, well, both models are scaling quite well, and they go out to the whole machine. And, okay, the curves sort of flatten a bit, but is that like, how much is that a real signal? Maybe, in fact, we're seeing this big discrepancy, and the GPU is a more appropriate architecture. So I like to plot things differently. This is back to the kind that we've seen before. So it's like a rate of work per node versus execution time per time step in the model. And we can see here that weak scaling is stationary. So if I move from the 19 kilometer model to the 3.7 kilometer model, I basically stay in the same place. There's a little bit suboptimal weak scaling when we go to 1.9. This point up here, we're going to the 0.93, but these are basically all along the same curve. So this is really useful to understand capability, understand those limits. So our perfect weak scaling always puts us along this curve for the GPU model, and it puts us along this curve for the CPU model. And you might say, okay, well, throughput's really important. We just have to be patient. The trouble is that these are very low number of simulated years per day. And so the left edge of the text is the point that matters here. So if we want 5 simulated years per day at 10 kilometers, we need to be over here. And that involves about a 3x reduction in latency for the GPU model. which is probably quite a tall order. Now, in this case, the CPU model was not well optimized for CPUs. Probably the CPU model can be optimized quite a bit more. Looking at other codes, that's likely a safe bet. But we've got kind of a bunch of um, the representative kind of at a given resolution, um, how fast do you have to go, and what throughput do you need? And so you can kind of look at those points. And if we zoom out a little bit, we can see the target resolutions, 1 simulated year per day or 5 simulated year per day. This sort of hypothetical is, let's keep the number of nodes fixed. That represents like what's the budget of a facility. But what do you have to do to move up on this chart? Well, we need Moore's law, or we need to buy a bigger facility. So continued sort of architectural scaling, move to 5 nanometer, et cetera, can help you move up on this. More efficient architectures, better chip design, it can help you move up on this. Just more money can also help you move up on this. The trouble is nothing gets you to move to the left. That requires looking at architectures that really can optimize for latency. It involves some amount of software to minimize latency, but architectures tend to have a kind of fundamental synchronization cost, and reducing that is really hard because usually like that's been important for a really long time, and that's not the way that kind of physics helps us out, that improved manufacturing process helps us out in. And so moving to the left is a really hard problem. Anyway, this sort of figure demonstrates our trade-offs in terms of capability. I call this a Pareto approach to capability. So the idea here, and you can apply it to basically any of the choices that you're making in computing, or in any other domain for that matter. And so the idea is you have multiple objectives. So there are things like model complexity. I would like to be able to solve more complex models. I would like more accuracy, like a smaller error. And that can be in terms of like a forward model, but also, in a much broader sense in terms of uncertainty quantification, in terms of design optimization. But anyway, there's a sort of a concept of accuracy and of how complicated the model is. And then there's the properties of how long do we have to wait? That's the execution time. And I think that's very usefully decoupled from execution cost, because these things are quite independent quantities. And so you can plot various configurations. You can imagine plotting totally different discretizations, different approaches to solving a problem. Those all generate points here, and sometimes you make bad choices and they end up way out here, right? The idea is we want to minimize both F1 and F2. And so some configurations are really things we don't need to pay attention to. They're not Pareto optimal. C here is not optimal in that sense, in that we can improve on both of the metrics. And so there's no reason that we should want to run C. We should always be pulling over to like A or B, right? So this can be used to assess trade-offs really, throughout our decision-making process. And I think this is the way that we should think about it. Now, I want to kind of talk about distortion a little bit. So on this previous slide, there were several measures of cost. And one kind of measure of cost is like node hours, like we have an allocation we're allowed to run here. The thing is, writing a proposal to a different facility, it can be a wildly different amount of work. It could be like joules. How much energy is consumed to do this job? that's a maybe a good kind of altruistic measure. Um, Ultimately, people tend to care about dollars, um, but these different sort of costs are not fungible, and cloud kind of makes them fungible. So funding agencies are putting their thumbs on the scale in a sense. They say, oh, well, we bought this big machine, and if you use that machine, and if you use it in a specific way, and I'll give you an example of that. This is, or the right panel here is from a poster from the Acme project. And what they did is they bundled together a bunch of runs. This was a few years ago when Mira was still the primary machine at Argonne. And the diagram here is showing how their queue works on Mira. So if you have more than 4,096 nodes, which means you're being, on Mira, it's all powers of 2, which means you're being billed for 8,192 nodes or more, then you can be in the production capability queue. And that both means your jobs can run for longer, so you don't have to pay repeated setup costs. You also are often prioritized, so those jobs may in fact start sooner. Whereas if you're running small jobs, 4,096 nodes and smaller, then there's the short and the long queue, both of which are only up to 12-hour runs and at lower priority. So in order to manipulate this queue, in order to run jobs that sit over in the capability queue, you either have to actually use all those nodes. The trouble is the model doesn't strong scale that far. It becomes significantly less efficient if you're running on that many nodes. And so instead they bundled jobs together. And Ray Loy is a performance engineer at Argonne. So this isn't just a user kind of gaming the queue. Instead, this is the facility working with the users to bundle together independent jobs and make them look like one larger job in order to get priority in the queue. And all of this is wasted effort. This is just burning time, human resources. You have the senior people on the project. David Bader is the director of the whole project. A bunch of other senior people there. Oops, sorry. It's just burning human resources in order to game the queue. This is really unfortunate. Like, there's got to be a more efficient way. So these sort of incentives of like, use this machine in a particular way, even if that doesn't really match to your science, this causes a distortion. It affects the way that we understand cost. And PIs may have a limited time to apply for, like, to spend time obtaining allocations. Sort of finding a machine that best matches the workload that they have. And so it's pretty common for people to sort of play this game, make their app look like what the facilities want the app to look like. A lot of costs involved in that. A kind of promising thing about cloud resources is that it's all fungible. It's all just money. And in principle, it's the same money that could pay for people. And so, if doing some code optimization is more cost effective than, paying for this many million hours, then you can do that. It's an easy choice to make. So let's think a little bit more about human time. There's an element of packaging and distribution, which is, it tends to be overlooked by full-time developers or people who are contributing to packages, especially in scientific computing. So just getting your software installed is a big hurdle for a lot of prospective users. If it isn't tested, it probably doesn't work. There are some projects that like try to help out with this, but it's been cumbersome and kind of slow going. Like, how do we test on a Cray? How do we know that it works with whatever the latest version of the Cray PE environment is? Usually that's like an individual developer or some user that's talkative enough and informed enough. They're going to go try to install the software. It's a manual process. There isn't like a public cloud Cray PE environment continuous integration. And because developers often know a lot of quirks, they tend to underestimate what is this cost, what is the impact on users. This can go even further where like a user experience is damaged because it's actually the user's fault. Like they have a broken environment, their compilers don't actually work, for example, but they don't know that they don't actually work because they haven't been building a bunch of other, say, MPI-based software yet. And so they go try to install a package, say Petsy, and Petsy says we can't use this compiler. It can't compile a simple program. But they think that it's our fault as Petsy. Sometimes they'll send us the logs. We can work with them. But this is a drain on maintainer time, and it's a bad user experience. And not all users are going to, send in their log. They're going to assume, oh, I'm doing something wrong, but I can't figure it out. I don't have time. And there's a user that we lose. And so I think it's quite important to be able to think about to be able to distribute software by working with packagers. So apt, RPM, brew, SPAC, all examples of packagers where in principle people don't have to think about it. They say install this library, this package, the dependencies will all be brought in. Some languages these days have really nice environments for that. Rust or Julia are kind of examples where you just say add this package and it'll go fetch dependencies and build them, and you don't have to think about it. It works reliably in practice. One of the cool things about SPAC that isn't really a technical thing, but more a like convention, is a lot of the software in SPAC is actually maintained by people who are upstream, who are the maintainers of that package. And this is rarely the case for apt and RPM and brew. Often those are kind of motivated users who are doing the packaging for the platform that they use. So one of the positive effects of SPAC is not SPAC as a way to install. I mean, there's that too, but that's separate. But just who's doing the maintenance, who has to deal with making the install clean and non-broken on a bunch of different platforms. And so that kind of drives home the importance of being able to automate. Then there's just building. So users build once per machine. Developers build continuously. They build incrementally. They build on different machines. They perhaps are part of many different organizations. And so time is often sliced pretty thin. This includes the developers of, say, libraries that are downstream. And ways to help with that are like stable binary interfaces, using programming constructs that can compile fast, making sure that accurate incremental builds are fast. And also not needing to build so much. So a lot of packages have configure time choices that need to be made, and that affects the build. And this means that to test some end user configurations, you may have to rebuild underlying libraries multiple times. This is a tremendous time sink for developers and users. Now, this quote from Matt Turk, he says the distinction between users and developers is actively harmful. And I read that many years ago and was like, this is a perfect way of saying this. And so we can design our platforms such that we kind of trick library users into becoming developers. And what I think is kind of interesting about this is we can do it to some extent in a technical way by creating things like plugin systems, by making it easy for users who are reasonably comfortable with the library but not experts to be able to contribute things that are really useful to other people. And so this is like a software architecture question. Users have their own incentives. They may not care a whole lot about like devoting lots of time to making the software better. But if it's a really low incremental cost, they're writing code for themselves, and just the recommended way to write code for yourself that doesn't incur too much complexity is in fact like sets them up to be able to contribute it so other people can use it, but also so other people can cite it. That's really what we're going for. And so there's a bunch of obstacles to this, like poorly tested code and software architecture where there's kind of the thing that the user wants to do is sort of cross-cutting somehow, and so they hack it for their particular environment. Users often don't think nearly as much about like what are the assumptions about the environment. However, if you can, as a maintainer, set things up, kind of predict what are some of the kinds of things that users are going to want to do, then you may be able to cut down on those kinds of assumptions. Designing for debuggability, having debugging tips be well documented, a lot of kind of input and output validation. These kinds of things can help a lot in making it so that when the user first gets their working code, it's actually not so far from what would be acceptable library code, and that they'll be willing to work through a code review. Of course, you have to be responsive in the code reviews. So this is kind of a big world of like, how do we build open source communities? How do we make this a positive interaction? There are technical things. There's also a lot of social things. Having a code of conduct, having constructive reviews, prompt feedback, having a good way of communicating things like testing and coverage, trying to keep things consistent, because maintainer time is always really in short supply. How do we empower these users who are potentially becoming developers? Say by having discussions in a format where people can weigh in, where people can understand the rationale. There's of course an issue there of bike shedding, where you have people who maybe don't have the experience to have a particularly informed decision about something, often about a relatively simple choice, and suddenly a lot of time goes into some thread. However, I think overall keeping discussions in public is really important. So there's a hindering back channels rule that has some kind of good thoughts on that. It's sort of the opposite of the Chatham House rules, which is like everything that we talk about stays private here. Some people are really concerned about scooping. So they say, well, I don't want to release this until the paper is out, because if we just like release this code, then somebody else could come along and write their paper about that. Then we don't get credit for it. My opinion is that this is really a social problem we should deal with social means. keeping that, like withholding those new contributions until you have a chance to write the paper, it slows things down. It significantly increases the cost of that development because the project's going to have moved on quite a bit by the time you get around to making that contribution, like to trying to merge it. And some large projects, in fact, when Acme forked from CESM, to some extent, you could say this is why. And I think it's a really costly technical choice. In science, our budgets are way smaller than in industry, and industry has underestimated this kind of cost frequently. So examples being like Google taking, they have a version of the Linux kernel, and back 10, 15 years ago, they did lots of work in a fork. Of course, then they were able to hire 10 times as many developers to help kind of pay that off and get a lot of these new features upstream, so that they're not maintaining such a huge difference from the upstream project. But in science, we almost never have a situation where we can go hire dozens of software engineers. Our compensation just isn't competitive with industry, and our projects tend to be smaller and much more fragmented. And so there just is, it's nothing like in industry where a startup becomes successful and suddenly they can hire a much bigger team. So I'm an end user. I'm at the top of the stack. This is basically what everybody says. Everybody who doesn't really know that they're doing a library, and yet it's almost never true. So for example, engineers take commercial software, script mouse clicks around those GUIs. So even when you're a GUI, targeting an end user, targeting that direct human interaction, this happens all the time. It's a horrible anti-pattern because there's always a higher level of the stack. We're doing uncertainty quantification or optimization or something that goes around the outside. And no matter where you are, you're not forever at the top of the stack. So another example, you don't put AMR into your application, you put your application into AMR. This also it makes it really difficult to interoperate with other applications. These are what I would consider to be anti-patterns. There's a bunch of performance traps. Like, we have to do it this way, static memory allocation only. This is still the case in NEC 5000. It causes a lot of complexity to bubble up. There's a, in my opinion, kind of absurd build system. I work with Paul on a regular basis. That choice is really baked in. It causes us a lot of grief, and yet they're committed to it. But it creates a lot of complexity and really slows down the development and contribution process. There's often a concern about indirect function calls. Can we have virtual functions or callbacks, or does that need to be template specialization? And very often, if you can pick the granularity appropriately, there's negligible cost to these, more dynamic kind of late binding constructs, and it makes compilation faster, and it makes much smaller binaries. There's other choices. There was a Gordon Bell issue several years ago where the author said, well, implicit solvers just don't scale. And what they were doing is running explicit diffusion instead, which is great for generating flops. And
horrible for actually solving the problem. So granularity is really important. I think one of the more kind of beautiful ways of doing this is the microkernels in Bliss. So this is an example where they've really thought through what is the bit that really needs to be optimized, specialized completely on the data types that are involved and the architecture that's being targeted. And that little bit is written in assembly. But with Bliss, everything else is done dynamically. And you can choose at runtime that you want to compute in one precision that may be different from the precision of the matrix arguments that are coming in. So you don't get that through the BLAS interface, but the when you call the Bliss interfaces, it's actually super flexible and performs very well, quite competitive with MKL. So comparisons are somewhere that I think we tend to be lagging in scientific computing of having like good comparisons that are widely used. So there's a few benchmarks that are well known, but often I would say they're over specified. And I would love to see more like domain application driven benchmarks. This Donahoe paper from 2015 is, it's like the 40 years of data science. And the big thing that he attributes to success in the machine learning space is what he calls the common task framework, which is basically setting up a benchmark at some appropriate level of abstraction where people can then compete on it. And we see this all over in the machine learning literature and in competitions like Kaggle's, which allow people to have a like reasonably high level of abstraction. I would love to see more of this in scientific computing. There's some examples here. The say parallel research kernels, which Jeff Hammond works on and is promoting quite a lot. Those are like completely specified, you know, it's like a small piece of a task, but it is useful. It provides a lot of feedback, but those are much more specified. Whereas if you move up to like Q-test for optimization, those are, again, fully specified optimization problems, but you can use very different algorithms inside of the optimization. So it's a bit higher level of abstraction. I would love to see more like verification challenges and validation challenges. And it takes some work to communicate that effectively, to design tests that, that are at the right level of abstraction, that don't admit a lot of cheating. Anyway, I'd like to kind of propose a way of thinking about these trade-offs. And I'll give a couple of plots and then wrap up. So let's suppose we have some kind of parameter representing problem size. And this parameter, you know, maybe it's the amount of memory occupied by the matrix, or you know, something about number of degrees of freedom, something related to like the size or resolution of our model. There's an amount of work, so that's a function of the n, and typically that amount of work is relatively independent of the number of processors. Sometimes you do extra work in order to, you know, say hide some parallel costs. But the execution time definitely depends on the problem size and number of processing elements. And so we have a rate at which that work is done. Sometimes I call this the throughput. There's an efficiency, kind of a rate per process. Often you want to do like rate per cost, rate per joule, something of that sort. And we see lots of benchmarks that report something like an Rmax. So this is the maximum rate over all of the n's. The thing is, with benchmarks like HPL, they get to choose the n. And in HPL, usually larger n wins up until you fill whatever level of memory is critical. And so people tend to run that n. It makes it really hard to compare this capability. But I'm happy to use Rmax. I'm just not that interested in the value of Rmax. So you compute Rmax by, say, running a study where you run different problem sizes. That sets this kind of baseline. And then this is a sort of notation that Paul Fisher and I worked on. And so the idea is n sub 0.8 is the problem size at which you achieve 0.8 of Rmax. It's the minimum such n. So this is the kind of smallest problem size at which you can achieve this respectable fraction of your peak efficiency. And the t sub 0.8 is how long it takes to execute that case. So this is like a practical measure of the latency. So this plot here, these are 4 different benchmarks from the SEED project. You can look at any given one of these benchmarks, and you can see, okay, well, there is a Rmax here. It's whatever this sort of, you can follow any single one of the curves. So there's a max, and in this case, it's not the actually the largest problem size on these CPU nodes. It's one that can effectively use the level 3 cache really well. But whatever, we have this Rmax, and so we kind of look at 0.8 of that value, and we're looking at what's the minimum size, and so you end up with something like this, and the size is around 100,000. And over here, our x-axis now is time. These are all the same points. So if I hover there, you can see over on the left that one of those boxes is highlighted. And I can come over here, that box is highlighted. And so that's kind of the sweet spot. That's where people that are concerned about latency but have a not infinite budget, that's what they tend to care about. And so working on improving those scenarios, and you can see the same kind of thing on any of the other lines. But working on improving those sort of configurations is probably the kind of most important thing to work on. This is just looking, these sort of plots can look quite different for GPUs because GPUs don't have this like level 3 cache that can generate a lot of reuse. And so this is an example on a GPU node. Here, they tend to just reach up to their peak performance and then flatline until you run out of GPU memory, which might not be very far. But we can see these sort of scaling curves. And some of the CPU points are over around here on relative to this curve. And so there is a sweet spot there in which the CPUs can significantly outperform GPUs. These are just like AMD EPYC. And that's a trade-off that, that people care about. I think I'm running over time, so I'll go kind of fast on this. These results are produced with libseed, which is a purely algebraic library for finite elements. Finite element library with no finite elements. There's no function spaces, there's just the algebraic properties. It's meant to sit underneath existing finite element libraries to be something that's kind of easy to incorporate. And so the domain of libseed, you see sort of here, libseed doesn't do the parallel computation, but it does from vectors that can fit within a single memory space. It does transformations to elements and quadratures, can evaluate nonlinear operators. It's fast for high order stuff. It's currently the the fastest methods available in MFEM. So this is an example of kind of one of our attempts to build something that ultimately is language agnostic. We're working on several different higher level interfaces. The Python one is fully usable. In addition to the C and Fortran have been available for a long time, but we're also working on Rust and Julia interfaces. So like language agnostic, minimal assumptions about the environment, able to target lots of different backends, single source code for implementing physics. And so anyway, if you're interested in that, check it out. And overall, I would say the way we think about performance and acceptable kind of burdens to pass off to users in scientific software shouldn't be different from non-scientific software. We need to reflect a lot more on that, be sort of harder on ourselves. Focus on modularity, extensibility, think a lot more about like how we build communities, how we can provide incentives and credit for developers and maintainers, and create benchmarks that are really useful for comparison. We'll acknowledge that the real world is much messier than those benchmarks, but I think we can create much better, especially higher level benchmarks. And sorry if I ran over time, and perhaps I can take some questions. Back here,
the main attraction
we've got,
with
Jewel, spelled like the standard unit of energy. She's 3 and likes riding her bike with no training wheels. Awesome. And rock climbing. And Neve, 4-month-old, is sitting in a chair. I'll bring her around in a sec.
Great. Thanks a lot, Jed. Thanks for your time. Thanks for the great talk. You actually talked about so many things that in the last few weeks we were discussing internally in the group. So I was wondering if you were, attending our own, meeting in the group, because you were echoing so many, things in your slide that we actually experienced, ourselves while, releasing some software or discussing performance, portability. And here's the main attraction of your talk. Great.
Wow.
Beautiful. Awesome. All right, so let's see if we have any question from the audience.
Not a question, but I really like N 0.8.
Yeah, so Paul really likes N sub 0.8, and I really like T sub 0.8.
Okay, yeah.
So the thing is, N sub 0.8 is an input parameter to your model, but it doesn't tell you anything about capability. And if you're comparing, say, nodes with like thin nodes to fat nodes, it doesn't translate very well. So if you imagine like you have a thin node, N sub 0.8 might be very small. And I mean, Paul says that's good, but if you have a fat node, it's okay for it to be, for N sub 0.8 to be proportionally larger. As long as T sub 0.8 stays fixed, that's all fine. And so N sub 0.8 is like, how do I design an input file in order to achieve this point? Whereas T sub 0.8 is more like capability.
It's vexingly indirect though, right? I mean, first you have to find Rmax, then you have to do, and then you have to do this. But it really crystallizes what you should be thinking. So I like it.
Thank you, Jed, for the nice presentation. And like Hatem, I was about to say, are you in our mailing list? So this morning we have the same thing like about Petsy, like the one who wanted to install his own Petsy, and we already have the flavor, and about the benchmarking because we need to work for Shaheen 3, and it was exactly the same question. So here I would like to probably when you will share the slide, because I didn't take note of all the paper that you have referenced. So probably later on if you can send it, especially where you showed for the capability. So we're working on trying to build some benchmark from our faculty. And the thing is also like how to balance between, we are like very similar to the model of we like nurse. So we have like hundreds of applications. And indeed, we have to serve both for capabilities and capacities. And here, this is like when I see like your site, okay, yes, and as like a computer scientist, I want to tend only for capability, but we have to, I would say, to make our investment, of course, and please all the faculty, we have to deal with both. So do you think that your study also we can transport it also for capacities for the other codes and how we can do it?
Yeah, I think it's actually more or less this, it's the same kind of analysis, like using a Pareto optimality sort of approach, I think is still entirely applicable. And I guess I would just argue for trying to like minimize market distortions, unless your goal is to get people to compute in a particular way. But if your goal is to, like, broadly speaking, advanced computational science to help people along, I would try to minimize the market distortions. In a sense, I would say the kind of policy like Argonne has on that I mentioned in that poster, that type of queuing policy is effectively subsidizing the most mature communities who can devote resources to playing those games. And I think that's exactly backwards, because I think actually the greatest gains in kind of high performance computing come from the less mature domains. And so it's not that the mature domains aren't important, but they already have a lot of resources. They already have pretty big advantages. And we don't need to be subsidizing them. And so, yeah, I would try to like adopt policies that make it a friendly environment for less mature, even like new HPC users.
Thank you, Jed.
I don't know to what extent that.
No, it makes sense. We are also like constantly like adapting our policy, and especially like Sabra is leading like the effort on IBEX. So we have another cluster where it's more towards like the AI community with GPUs, while Shaheen, we try to keep it both for capacity and capability, but with more, I would say, like room for our hero jobs, I would say.
Sure, yeah. And there's an element of that, like, it's sort of advertising to be able to get those hero jobs, to make them run. Because like that is a way that you get recognition. You get those, like, SC papers and such. And so it increases visibility for a facility. But I guess what I see at DOE is a lot of the LCFs are kind of prioritize that beyond things that would more benefit the science they intend to be supporting. And it's easy to see how the incentives encourage that, but I don't think it's constructive.
Also, like, for example, you said like there is a high impact with this hero job about what I see. Also, like what we have observed at Chaos, like even for these small small jobs, but they were very successful in very nice, I would say, like in the domain science with a lot of publication, like in Nature and so on. But the aspect of HPC is somewhere like, I would say, not well done as a PR, while the community that is doing only capability, they tend to talk a lot about that. So do you know, like, I don't know if it is the case in the US where in DOE lab, I know they focus only on large scale, but do they talk a little bit about the impact also of this? capacities jobs.
Oh, I mean, they certainly do, and there are lots of people who get it, and the facilities are not. They don't all have the same policies, but to a large extent, Oak Ridge and Argonne, which are the leadership class facilities, tend to incentivize larger jobs and the more like heroic scale. NERSC much less so. NERSC's mission is explicitly like supporting those smaller groups. There is a NERSC has a kind of useful dashboard of like queuing times.
Oh yes.
There's this like historical queue wait time. Let's see if I can just load it up here and share.
Does NERSC used to publish, Kathy used to publish a histogram of frequency versus number of nodes.
Yeah, so the top here is the queue wait time. Number of nodes requested is on the vertical. So, and then this is the number of hours, like, you know, how long do you want to execute for?
Yeah, this is something a user would want to know, but I'm more curious about a less granular thing where, you know, it's just over the years, she shows how when a new system is introduced, users gradually start figuring out how to use more and more of the nodes in a capability way. And I love the slide, but my last version of it is probably about 8 years old or something. So do you know if there's a new version of that? Have you seen that?
I don't know.
Okay. Anyway.
Yeah.
Actually,
but here you can clearly see the sort of perverse incentive that shows up sometimes, where, you know, say if you're looking to run on a one node, sorry, you're looking to run for 1 hour, submitting it on 2 tends to have a shorter queue time than submitting on 1 node. But this Argonne doesn't publish an equivalent sort of table, but it's worse in a sense, in that submitting a larger allocation or making a larger job submission will very often, like almost always, make it run faster.
Well, this is a very nice graph for our class use. Like some people are waiting more than 20 hours. So, so this is nice. Be more patient.
Yeah. I wish that all facilities published things like this, but also looking at this sort of table explains why a lot of individual researchers are interested in using cloud computing, because now if they can pay for the time, like if you're running relatively small jobs, not for super long periods of time, then it may be quite affordable compared to the human time. And, you know, so if your jobs start basically immediately, that's quite attractive. So.
Yeah. Great. Jed, thank you so much again. It was a great time with you. We'll let you go back to your busy mornings.
All right. Yeah, thanks so much. This was great. And
thank you. It was great for us.
If you want to follow up, it sounded like there was some an email discussion maybe you wanted to loop me into. Sure. I can't promise a lot, but I can. Feel free to CC me and I'll participate.
A little of Jed is a lot. You can quote me.
I will. All right.
Thanks.